Problem 1. Each plate of an air-filled 4.65 microfarad parallel plate capacitor stores 67.6 microcoulombs of charge. We want to A, find the potential difference across the plates in volts, and B, we want to know how much energy is stored in that capacitor. So let's solve this. So the first thing we want to do is we want to list the things that are given. So what's given here? We have a capacitance that's equal to 4.65 microfarads. We also have a charge. The charge is equal to 67.6 microcoulombs. And what we want to find is the potential difference. And we would also like to find, that's for part A. In part B, we'd like to find the stored potential energy on that capacitor. So these are just some of the things we want to find. So let's go on ahead and solve this. All right. So for part A, if we want to find the charge, or not the charge, but that potential difference, we can do that by looking at the equation for the charge. We know that the charge is equal to the capacitance times that potential difference. So we need to isolate potential difference in this equation. So the potential difference is equal to the charge divided by the capacitance. Remember that our charge, I'm going to leave it in microcoulombs, is 67.6 microcoulombs, divided by the capacitance, which I'm going to leave in microfarads, which is 4.65 microfarads. So when I do the math, I get 14.5 volts. This is my potential difference. Now, the next thing I need to find, well, I want to find the potential energy stored in that capacitor. So PE sub C. Well, I know that I have a potential difference, I have a charge, and I also have a capacitance. So there are a few things that I can use. So if you remember from our talk in the lecture video, the potential energy stored in the capacitor, let me write this in a different color. So that potential energy stored in that capacitor is equal to 1/2 Q times delta V, which is also equal to 1/2 C times delta V quantity squared. And that's also equal to Q squared over 2C. All right, so all of these gives us the potential energy stored on that capacitor. So I know I have a few things. Well, here I have the potential difference. And then I also have the charge. We know that the charge was equal to 67.6 microcoulombs. So I'm going to use this first equation here. So this is the one that I want to use. Okay, so PEC is equal to 1/2 Q delta V, which is equal to 1/2. So we have the charge, which I'm going to convert into coulombs, 67.6 times 10 to the negative 6 coulombs, times the potential difference, which is 14.5 volts. This gives me a stored capacitance of about 0.00049, what is it, 0 or 491 coulombs times volts, or if I put this in scientific notation, that's 4.91 times 10 to the negative 4 joules. Remember, when we talk about units, okay, the joule is equal to, or we'll say the volt is equal to a joule per coulomb. So a coulomb times a volt is equal to a joule, which is why we got these units here. Okay, so just two very different ways to do that. We could also solve this same thing by using a different equation. So we can say that the potential energy in the capacitor, we can use the other equation. So let's go and let's use this one over here, is equal to Q squared over 2C. Well, we get 67.6 times 10 to the negative 6 coulombs, quantity squared, divided by 2 times the capacitance, which is 4.65 times 10 to the negative 6 farads. This also gives me 4.91 times 10 to the negative 4. And in this case, we have joules again, because we have coulombs squared, okay, over farads. Okay, so that's coulomb squared over farads. That gives us coulomb squared divided by a coulomb per volt. This is coulomb squared times the volts per coulomb. This gives us a coulomb times a volt, which is equal to a joule, which is what we have here. So that's how you would solve that. And you can try the other equation if you like to see if you get a similar result.